So finally, the last video in this learning sequence, let's talk about how to make PLS-DA model and how to investigate it. You can see that I copy-paste part of the code from the previous script where I create the calibration and test set. However, for the calibration set, I need to do one more thing. You remember that we have three classes in calibration, and I want to make a PLS-DA model only to discriminate between versicolor and Virginica. So let's limit the calibration set by these two classes. First of all, I need to make let me create an int. It's an index vector, and then I simply compare. I say CC should not be equal to the class Setosa, right? So I don't need Setosa here. And then I simply say XC, select everything from XC where int is true, right? And then I will do the same for CC. So that will help me to get only the values which are from Virginica and versicolor. However, there is a little trick here. So if I run it, you can see indeed that I have 80, not 120 anymore, and also in CC. But you can see that if I run CC, although I have only Virginica and versicolor here, I still have three levels here, right? And this can be quite misleading when you use it. And therefore, what you can do, you can use a special how do you call it, the function in R, which allows you to drop levels which are not present in a factor. So if I run it now, and then if I look at CC, you can see I don't have Setosa anymore because I simply don't have values corresponding to Setosa. So that's a little addition here. And now let's create a model, PLS-DA. In this case, we provide the XC and CC, so it's a calibration, X calibration, and CC, it's important, it should be a vector with factors. So I have two classes here. How many components? Let me use like up to 3 components, for example. And then that's a good thing about PLS-DA. You can use the same, for example, cross-validation, because strictly speaking, PLS-DA, it's PLS, it's regression model, so we can use cross-validation here. Let me just, for the sake of simplicity, use full cross-validation. Then I will also scale the data, so I say scale equal to true, and then I will ask for summary. Okay. So let's see how it works. You can see that we got a summary, and summary, I mean, because I have two classes, so to speak, PLS-DA creates like two models, but they are sort of mirroring each other, right? For example, you can see this is a class versicolor, and then all statistics for versicolor, calibration, cross-validation, and this is class Virginica, and then all statistics for Virginica, calibration, and cross-validation. But of course, I mean, they are sort of almost identical, right? What else is important? You can see that it was found out that 3 component is important. Let's check if it's indeed correct. So let's look at the for example, misclassified samples. How many samples misclassified? Let me use a bar plot for that. And then let me also add the labels, show labels equal to true. And then you can see that indeed seems to be that 3 components is best, because it allows you to get the smallest number of the misclassified samples. Also, when you use cross-validation, you can see 3.75% is misclassified, while here we have 5% and here we have 10%. So in this case, let's stick to these 3 components, right? And then, as I said, you can use all these predictions, for example, prediction plot for similar to what we have in case of Simca. You can see we have 2 classes, versicolor class, Virginica class. You can see that among versicolor we have 1 false negative here and false positive here for Virginica, and then we have also 2 false positives in versicolor and 2 false negatives in Virginica, right? You can also see this here, so 1 and 2 and 2 and 1. I forgot to say that by default it shows the cross-validation results. If you want to see calibration results, you need to ask for that explicitly. By default, it shows cross-validation results. Okay, the prediction plot and some others again. Okay, for example, you can make a plot residuals. Let's say X residuals, right? And then you can see that indeed we have a pretty good. We don't have at least any outliers here. Let me just, for example, I can color group them, right? By CC. Not predictions, residuals color group, of course. Sorry for that here. And then let me move it down so I don't confuse myself as well. So you can see that this is Virginica, this is versicolor, And then you can see that, I mean, there are some Virginica samples that are extreme for the model, but in general, I think they look pretty good. Remember, this is not like in Simca, right? We don't make a model, separate model for versicolor and Virginica. It's a joint model. So it means that all these samples should be like inside here, right? What else? Yeah, I can also make, of course, the, for example, the plot regression coefficients, right? Regression coefficients plot. So you can see that, for example, if you look at the regression coefficients, these two seems to be the most important ones. I can also add the confidence interval, of course, and then you can see that indeed seems to be these are the most important. Also, these also are important, right? But at least from the coefficient, from the confidence intervals point of view. But it seems like these two, petal length and petal width, I remind you that this is the last two. These are very important. You can actually also use all the variable selection techniques. For example, you can use plot VIP scores, M, and then you can see the VIP scores. Let me use the bar plot here. I think when you have that few variables, bar plot is the best. So you can see that VIP scores also, these two have the biggest VIP scores, right? You can use plot selectivity ratio, M. Let me also use the bar plot. And then you can see these two also very clearly have a selectivity ratio. Actually, the results for variable importance are very similar to what we also have seen in Simca when we did this discrimination plot, right? So these two, petal length and petal width, these are the most important variables, okay? So all these tools are still available, so you can do variable selection. You can even do IPLS for that, but in case of IPLS, you need to use the predicted values, not the classes, okay? And then, for example, if you want to get the predictions, let me just make the following. Let me show you the results, and then let me show you the CV results. Okay. So you can see that this is cross-validated results for PLS-DA, and then you can see that actually what they have. They have the predicted vector array with predicted class values, reference class values, all the statistics. You can get everything. For example, if you write, for example, true positives, you will see a vector of true positives, right, for every number of components and for every class, okay? But what is interesting is the predicted values. So you can see the predicted values. It's an array, and it's an array because you have like certain number of observations, it's one dimension, you have number of components, it's a second dimension, and then you have also two classes, Virginica and versicolor, it's a third dimension. For example, if you look at the class versicolor, you can see that if we use, for example, three components, you can see this is +1, so it's versicolor, and then you can see this one is probably misclassified, right? Then you can see all of these are -1. So you can see that that's the result of classification, right? And then you can see the same here, Virginica, and then you can see these are -1 and these are +1. Of course, it's a regression model. So in fact, you can see the predicted y values. Look, it's the same array, but you can see, for example, why this one was classified as 1, because it's 0.7, it's positive, right? So you can see all values here are positive values, and this is a negative, so that was the false negative here. And then you can see all values, most of the values here are positive values. So that's actually what PLS predicts. These are predicted y values, and then we simply use a threshold. For example, if you want to make your own PLS-DA, not with 0 threshold, but you want to make threshold a little bit larger, a little bit smaller, then you can simply extract the predicted values like I've showed you here, and then actually use them and do your own manual decision about the classes. That's one thing. The second thing, I forgot to mention it in Simca, for any classification model and for any classification results, you can get a confusion matrix. It's a kind of the results. It should be results M, for example, res, and then CV. Okay, so it's a kind of confusion matrix because you remember confusion matrix is like a 2x2 matrix, right? Yes or no. But in this case, we have like class 1, class 2, and then none. So you can see this is a kind of confusion matrix here. So for example, all these rows, all these 40 observations were from versicolor class. 39 were correctly classified as versicolor and 1 was classified as Virginica. Then here we have all these rows are from Virginica class. You can see that 2 were classified as versicolor incorrectly, and then 38 were classified as Virginica. And you can also get this confusion matrix as for the Simca. You can for example, save it. So it will be just a matrix. You can see it's just a matrix with names for the columns and for the rows. Okay. And then finally prediction. So let me use this test set validation. You remember that we have some it's not very good test set because we have classes from the other we have observations from the third class, right? Let's look at the results first. Plot predictions, and then you can see results, and then you can see that indeed all these observations were predicted as versicolor, right? Also they are from setosa. But look, if we make a plot, for example, the x distance plot, the x residuals plot, right, the distance plot, and then, for example, look what I'm going to do. I'm going to say, show me the results for calibration set, $res calibration, and then show me also the test, right? The test. So it will show me the two, let me see, it should be like this, okay, and then list, okay. So here we go. So you can see that this is calibration and this is test, right? And then you can see some of these objects from the test that they are completely out of the, they are outliers, right? And then you can imagine that these objects are actually the setosa objects, right? How we can show that? Let me make another plot. Let me make a plot only for the calibration set first. Let me use this rescal, okay? And then what I'm going to do, I will simply change the limits so I can see all the values from let's say from 0 to 30 here, and the y limits from 0 to 25 like I have here. So y limits is from 0 to 25, right? So this is just a calibration set, right? And then I will also, let me do it like this, okay, like this. So this is the calibration set and this is the limits, right? And then now I can add the residuals plot for the results for the test set, but in this case I can also color group them, C group by CT, right? So I will see what is what, and then I need to make this little trick, show x is equal to false. That allows me to add these points, the colorized points, to the previous plot. So now I need to run this path, and then you can clearly see that. And then one more thing, I will make this gray, otherwise the blue color also used for setosa, right? So now you can see that indeed we have gray points, it's our calibration set, we have these red and green points, and all these points are recognized by the model as a good ones, right? So we have some extreme values, but we don't have any outliers. However, setosa, the observations for setosa, they are outliers because model knows nothing about this kind of objects, and therefore you can simply find out that these objects should not be used with this model. You should remove them from the test set because you can actually apply model to your test set. So this is the distance plot is very efficient tool, and then make sure that every time you make predictions of the new samples, make sure to test, to see, to find out if actually these new observations, they follow the trend that actually calibration set has. So the model was trained for, okay. So I think that's actually it. Now you know everything to start at least using PLS-DA also for your own data. And that's all for the classification part.